Hello everyone, my name is Kecheng Lu from Shandong University. I'm presenting with Mifeng from Twitter. Our talk is titled Palette Tailor, Discriminable Colorization for Categorical Data. This is our agenda. Categorical data are everywhere and represented by different kinds of realizations. In many cases, colors are used to include their corresponding classes. A major challenge is that the palette or the assignment to classes might not allow users to visually discriminate different classes in the given data, which makes discriminable colorization a very important topic. Given a marked class scatterplot, the colorization consists of two steps. First, selecting a good palette using existing tools. And second, assigning the palette colors to the classes. However, a random assignment might put similar colors together. Using discriminable color assignment can solve this problem, but it is based on a given palette. So a method that involves color creation to automatically generate a discriminable colorization for given data is necessary. To achieve this goal, we proposed a fully automated approach for creating and assigning color palettes to different realizations with high discrimination quality. We implemented our measure for a demo system that is presented on an interactive website. Now I'll briefly introduce some related works. The coloring of realizations contains two steps, palette generation and color assignment. We use three state-of-the-art methods, Tableau 10, categorical, and colorization from Chen et al. For this coloring process. For the Tableau approach, palette generation and assignment have to be done manually. For categorical, the first step, palette generation, is automatic, yet the color assignment step is manual. Colorization is fully automated, but the inaccurate class distance measure and limited color space often result in undiscriminable realizations. Here comes our approach. Let me first formulate our problem. Given a dataset X of M classes with a background color C0, our goal is to find a color palette which maximizes the class discriminability with respect to a carefully designed scoring function. We design our method based on both data space and color space. Data space contains a geometry-based class separation measure, while the color space is based on the CIE color difference and color name distance. We use them to quantitatively incorporate point distinctness, color discrimination, and name difference into our objective function. Given the input dataset and background color, to find the best palette in the infinite color space, we use a customized simulated annealing algorithm to rapidly generate a good result. Now let me introduce these three factors. Point distinctness is based on color distinctness and spatial distinctness. It measures the separation between neighboring points from different classes. We use this format to model class separability. However, in the original definition, Wang et al. Used the KNN graph to find the nearest neighbor. This might result the problem that the neighborhood omega of each point xi does not include all neighbors, thus it may lose local information. To overcome this issue, we propose to use RFShape as a substitution for the KNN, where RFShape constructs the neighborhood that includes all neighbors nearby. Color discrimination aims to measure the minimum color difference between each pair of colors from the given palette. Without this term, classes with small overlap might be assigned improper colors. For example, say the green and lime green classes that are hard to distinguish. In addition, we take background color into account by comparing it with each color of the given palette. Without this term, some colors might be hard to distinguish from the background. With this measure, the results with different backgrounds are all discriminable enough. Name difference is used to measure the similarity between colors based on naming patterns. For example, the two colors named blue have a small name difference, while they have a high discriminability. Different color names lead to a large score, such as red and blue. We formulate the name difference as the mean score between all pairs of colors of a given palette. Due to this color name distance, we can create palettes with different color names that help users to describe realizations easily. In order to accelerate the optimization process, we use a customized simulated annealing algorithm. We first generate a randomly initialized palette, as shown on the right. Then we disturb the palette to find a new solution. Simulated annealing will accept bad results according to the temperature-dependent probabilities. We record the best result during the process, and this way get to a satisfied result. We extended our method to different chart types, such as line charts and bar charts. Given the input data, we first discretize it, thus they can be treated as special scatter plots. Then we colorize these data points in the same way as shown before. Next, me will present the following sections.
Now let's go to the evaluation part. We wanted to know how effective our approach is at producing discriminable and aesthetically pleasing palettes. So we conducted a user study on Amazon Mechanical Turk that involves 155 participants. We tested out palettailor on 2 visualization types, 4 types of tasks, and compared it with the 3 state-of-the-art palette generation methods. The study includes 2 experiments, scatter plot and line chart, and here we start with the first one. The experiment has 3 tasks, 2 discrimination tasks and 1 performance task. The first task is counting class numbers. We asked the participants to answer how many classes were presented in a given scatter plot and let them to choose the answer from several options. The second task is comparing class centers. Here we ask the users to judge which of the 2 specified classes had a higher center. The third one was user preference. The participant was asked to choose the plot they preferred from 2 identical plots with different palette check conditions. And we compared palettailor with 3 state-of-the-art methods with different levels of automation, and our approach is fully automated. In our experiment, to fairly compare palettailor with existing manual approaches, for example Tableau, we set 2 benchmark conditions representing the systematically simulated best and random cases resulting from the manual coloring process. Similarly, for categorical, there are 2 conditions. And for the fully automated methods, each has 1 condition. That results 6 conditions in total. And we had 5 hypotheses. For the discrimination tasks, first, palettailor's results would not be worse than the best case conditions resulting from the simulated manual process, and would be better than random case conditions as well as the fully automated condition. And for the preference task, palettailor's results would not be worse than the designer-crafted palettes, and would be better than auto-generated palettes. We used 30 different generated datasets and careful between subjects design for the study. In this table, each row means a different dataset or different kinds of scatter plots. Each column means a different condition. Each cell means a specific group that a participant is assigned to. Each participant performed only 1 task and assigned to 1 group. This covers all the conditions and datasets and minimizes the learning effect. We recruited 105 participants from AMT for the experiment. Each participant went through 3 phases: consent and instructions, training, and then main task. The study results show that, in terms of discrimination tasks, palettailor is not worse than the best case conditions resulting from the simulated manual process, and it is sometimes better than the random case conditions. and palatator is consistently better than the fully automated conditions. For preference task, this chart shows how palatator performs against benchmark conditions. A value greater than 0 means that palatator is preferred over the other solution and vice versa. We found that palatator is preferred over the conditions of the manual crafted palette, and yet is not always preferred over the conditions of the auto-generated palettes. In the second experiment, line chart, we applied a similar experiment design. There are a discrimination task and a preference task, and here we briefly show the results. In general, palatator's results in terms of discrimination are not worse than the palettes generated from the manual process, and are consistently preferred over the results of the manual crafted palettes. Recall the high-level question that we had for the evaluation. From the user study, we found that palatator as a fully automated approach generates color palettes that are comparable with the state-of-the-art approaches in both discriminability and preference. And it consistently generates palettes with a higher discrimination quality than existing fully automated approach.
We also developed a system to assist users, and now it's available online. In conclusion, we proposed a data-aware approach based on simulated annealing for automatically generating color palettes with different visualization types. Then, we quantitatively evaluated the resulting color palettes and visualizations from an online user study. We further developed a demo system for interactive palette generation that is freely available on the web. More details can be found in our website. The system and data are available to use. Thank you for listening.